Okay, welcome everyone. My name is Franzke. I'm a group leader at ICCP and a professor at Pusan National University. And it's my great pleasure to introduce to you the ICCP research team on Earth system sensitivity. The title of my presentation is Unprecedented Climate Extremes in a Warming World. Many of my ICCP colleagues are involved in this research team, and we also have many former members of ICCP which still collaborate with us, and we have many international collaborators, for example, National Center for Atmospheric Research. In my presentation, I want to focus on two main research questions. First, what causes weather and climate extreme events? And second, when will the shifts of those extreme events due to enforcing start to emerge? So in a warmer world, we expect to see changes in extreme events, say the intensity and frequency of occurrence, for example, drought events, storms, and many other types of events. And this will lead to changes in the whole distribution of those variables. And this also might lead to the emergence of unprecedented conditions to which we humans and also many ecosystems might not be adjusted to. So how do we try to understand this? How do we try to estimate those changes in the distribution and to elucidate the underlying physical mechanisms leading to those changes? For this, we use climate simulations. I will mainly present here results which we accomplished in collaboration with NCAR using the Community Earth System Model version 2, for which we ran a large ensemble of 100 ensemble members on our supercomputer Aleph, and we used a particular scenario for future evolution, SSP3 7.0. Using CSM2 has certain advantages. One, it has an interactive lake model with improved mixing and lake ice representation. Another advantage is the land model, CLM5, which has improved soil hydrology and also improved fire scheme. Fire is also a topic we are very interested here at ICCP, and in those CMAP type simulations, which are concentration driven, like our large ensemble, we can only understand part of the whole interactions between climate and wildfires. So to actually systematically study those interactions in more detail, we actually use a more advanced version of CSM2 2.2. This has the advantage that the fire emissions can actually be transported into the atmosphere, but CLM5 only uses fire climatology for lightning climatology for wildfire ignitions. In order to also have there the interactivity, we also developed a new interactive lightning scheme here at ICCP. Okay, let's come to some of our research. So I will focus here on three partly connected topics: research topic, lakes, droughts, and wildfires, which we all studied in quite detail here at ICCP, publishing many papers. But I don't have that much time to go to all of them, so I selected a few based on scientific innovation, our collaboration, and also societal impacts. Those three topics are, of course, important for ecosystems, water security, food security, and they can also feed back onto climate, for example, by carbon release or aerosol releases. Okay, first I want to present some results of lakes, which we researched in quite detail, but here I want to just show one example on lake temperatures and when they might reach unprecedented conditions. That's research which was led by our former colleague Lei, who is now a professor at Capital Normal University in Beijing. Using the large ensemble for the first time, he was able to show basically the time of emergence of unprecedented temperature lake conditions to which ecosystems might not be adapted to. Here, if we look here at the time series for one particular lake in the western US, we see, so we can estimate using the large ensemble, the range of natural climate variability indicated by those two lines. And about year 2050, we have this onset of unprecedented temperature conditions. Or we can also call them no analog conditions, and that occurs at global warming levels of about 2 degrees. So this is one lake. We can look at the whole globe of lakes, which are represented in CSM2. And the color coding indicates the global warming levels at which those lakes might start to experience unprecedented temperatures conditions. In general, we find that in warm lakes, more in tropical regions, we have early emergence at warming levels somewhere between 2 and 3 degrees. Colder lakes, more at higher latitudes, we see late emergence, somewhere between 3 to 4 degrees of global warming. The early emergence, basically at warmer lakes, occurs because relative to the global warming signal, the amount or the range of internal variability is relatively small. So that's a signal to noise ratio problem. And at higher latitudes, we just have much larger amount of internal variability. Okay, lakes are of course also very important freshwater source, drinking water source, but they can also dry run. So they can contribute to drought conditions. Also a topic we extensively studied ICCP. So we looked at land-atmosphere coupling, multi-year predictability, as Axel already mentioned. But today I want to show you some results of day zero drought conditions. In 2018, Cape Town in South Africa basically ran out of water. That is what we called day zero drought conditions. They had to ship in by trucks drinking water so that people actually could survive. So the water availability typically is determined by precipitation, evaporation, river runoff or runoff, surface runoff, water consumption, consumption by us humans, for example, and also groundwater capacity. Global warming will lead to increase in evaporation, and in certain areas it might lead to a reduction in rainfall and runoff. So, motivated by the conditions in Cape Town, we were interested to see when and where those conditions might also occur elsewhere. So for this, we also used the large ensemble. We developed a new probabilistic detection attribution method based on fractional attributable risk. That's research led by our PhD candidate Vetchia. Here displayed in this map is basically the decade of time of first emergence. So the color coding indicates then the different decades. And in general, we find Southern Africa as a hotspot and around the Mediterranean. Just two examples, say the city of Spain, according to our simulations and analysis, might run out of water by 2030. City of Maputo in Mozambique might run out of water sometime, maybe 2040, according to our simulations. So we also looked a little bit at the societal impact, looking how many people are actually at risk of exposure to those conditions. And we find that about 750 million people by the end of the century are at risk of this exposure. That's about 9% of the total population. And also, especially urban population is at high risk of exposure to those conditions. So drought conditions can also contribute to wildfire activity. That's also a topic we extensively studied at ICCP. Here I want to show you two research results. One on permafrost interaction with wildfire. That's research led by my colleague Inwon. So looking here at the subarctic region, just picking out one typical grid point here in Siberia. We see here fire counts and burned area, and we can see that until 2040-50, not much happens, and then we have this sudden onset of fire activity, which then also intensifies with further warming. This is highly correlated with thawing of permafrost, which we can see here, the loss of permafrost. So that kind of hints that there might be a causal link. Just to briefly explain this, here on the y-axis, we have the soil depth, and the x-axis, the time axis. If you look here at temperature, at about 2040-50, we have this transition from freezing temperatures to positive temperatures. At this time, of course, we have a loss of soil ice, so the liquid water either goes further down into the ground, or there might be a surface runoff. So that means we have drying conditions in the upper surface layers, soil layers, which then makes for much more favorable conditions for wildfire activity. So we are interested in studying this climate-fire interactions, but that's basically as far in those typical CMAP type simulations as we can get, since they're concentration driven. But of course, if we have increased wildfire activity, we have increased emissions of carbon, of aerosols, which can then feed back on climate conditions. For example, they can affect the radiation budget, or they can also affect the lightning activity. So in order to simulate this or systematically study this, we use CSM 2.2, because this allows the transport of the fire emissions from CSM 5 into the atmosphere component, CAM6. And in order to really close the loop of interactivity, we also developed a new lightning scheme. That was done by our former postdoc Vincent, who is now a researcher at the Barcelona Supercomputer Center. I now show you some results which were just published last week in Science Advances. Here changes in lightning. Overall, we see an increase in lightning activity. Only here, Latin America, Southeast Asia, we see a reduction. Now you might wonder, we developed a new lightning scheme. How good is this actually? We compared this with some other commonly used schemes in other climate models, and our scheme is about 43% better, which is not bad, I would say. Then we see this change in lightning. We can then also look at changes in burnt area. Here we also see overall an increase in burnt area, which is partly to this lightning activity changes, but much more important are fire weather conditions and also vegetation growth in our simulations due to CO2 fertilization. And that, of course, also leads to changes in fire aerosol emissions, which we can see here, this increase. And now we can actually look how is this feedback on climate. So now we can look at the direct fire aerosol radiative effect and compared with our pre-industrial or control simulations, we see about 20% relative change in those radiative effects. Okay, coming to the end of my presentation, I just want to show you two examples of some ongoing research works. Something I'm very excited about is our work on climate impacts on infectious disease spread. So here we already worked on malaria, time of emergence, using our large ensemble, looking at extreme events, how they might change in the future, especially for Africa. And currently we develop a tick-borne disease model. Ticks occurs on all continents on Earth. They are the vector which carries the most zoonotic diseases. Some of them are very nasty diseases. And the research to understand how they actually might respond to climate change is just starting. And another very exciting research area, as already my former speakers talked a little bit about, are kilometer scale simulations. That's in collaboration with the Alfred Wegener Institute in Germany. We already finished 9-kilometer globally resolved simulations. Now we look at extreme events, how they behave in those simulations, cloud feedbacks, many other topics. And currently our supercomputer Aleph is running hot with 4-kilometer simulations. Okay, thank you very much for your attention, and I'm happy to answer your questions.